Welcome, I'm Kevin King. In this, the second of our series of 6 INRO training videos, I will explain some of the relevant hardware relating to INRO operations. This presentation builds on information from our INRO guidance videos, so if you've not already done so, you might benefit from watching the equivalent INRO video presentation first. We will start by looking at this INRO system schematic, which shows the options available for a single section INRO application. As you can see, the implement module is the core of the system to which all other devices are connected. The INRO implement module is very similar to the INRO version, but has a greater number of inputs and outputs, requiring some different connectors. We'll take a quick look at each of the connectors in turn to highlight any differences from their INRO counterparts. The directional valve outputs allow all the functions of an INRO system, but with the addition of a timed centralize and retraction valve output, which is useful in through-shift applications, and also 4 valve outputs that can be used for automatic implement frame leveling. There are 2 additional connectors for leveling sensor inputs to control the corresponding leveling valve outputs. One connector is for the right top and bottom level inputs, and the other is for the left top and bottom level inputs. The 2 camera ports are identical to those fitted on an INRO implement module. Extra camera ports can be fitted by special request. INRO systems typically have more CAN devices fitted than on an INRO system, so an additional second CAN connector is provided. INRO modules have 2 rather than 1 lift input channels, and as well as 2 proximity pulse wheel odometer input channels, there are 2 incremental encoder input channels. This reflects the importance of accurate odometry for INRO applications where visual odometry alone is rarely accurate enough. The console connector and console cable are the same as those used for INRO applications. The console itself looks the same and mounts in the same way, but is loaded with the computationally more demanding INRO software. Like INRO systems are modular and can be configured to control multiple independently steered sections from a single console. This schematic is of a triple section system, shown here in action fitted with electric rotors, or in this example with reciprocating blades demonstrating the flexibility of our systems. Now we will have a look at some of the devices that can be connected to our INRO modules via the CAN bus. We will start with the Tillett & Hague electric rotor. The unit consists of a 42 volt brushless electric motor and a reduction gearbox housed in machined aluminium casing with O-ring seals specifically designed for the agricultural environment. It has a top speed of 6 revolutions per second and has the torque capacity necessary for shallow cultivation of virtually all agricultural soils. The rotor is a sealed unit with a status LED at the front for rotor status, setup and fault diagnostics. It is waterproof, but it will not withstand direct pressure washing. A button mounted to the rear of the rotor facilitates setup on the CAN bus, without needing to open the rotor assembly. A single cable with 42 volt motor power, 12 volt power and CAN bus communication cores allows for easy connection to our rotor loom. Rotary blade profiles are available to cover a wide range of crops. Though it's often possible to use one compromised blade profile to cover a range of crop sizes. Rotary blades can be easily changed for different crop situations, using standard 90mm tools, as shown here. Later in video 4, we will explain how to choose a correct cultivator blade for a given situation, and to set the rotors up on a machine. Each rotor cable connects to a distribution box as shown here. These junction boxes provide 42 volt power from a 42 volt power pack, and 12 volt power and a CAN bus data connection from the implement module. 3 variants of the distribution box are available. Version A being the initial power and communication entry point. Version B is an intermediate junction box, of which there are normally several. Version C is the last junction box of the circuit, which incorporates a CAN bus terminator and a blanking cap. Customized cable lengths for these junction boxes are available. The power required for electric rotors depends on the soil, operating depth, disc size and speed. However, 150 watts might be a typical average load. A source of 42 volt power therefore needs to be provided that can deliver this power with some extra margin to deal with the peak loads from rotors, which are limited by overload protection at 420 watts. If the tractor already has a suitable power supply, that's great, but more commonly it's necessary to add a 42 volt power pack. The most economic way of achieving that is based on using 3 12 volt automotive lead acid batteries charged by a vehicle alternator fitted with a 42 volt regulator. We can advise on how to source an appropriate alternator and regulator. For maximum efficiency, that alternator would be driven mechanically from the tractor, probably via the PTO shaft. Alternatively, with some loss of efficiency, it's possible to drive the alternator from the tractor's hydraulic system, which can be easier and cheaper to engineer. We can provide details of an appropriate design or even a complete unit if required. To connect most CAN bus devices, you'll need a CAN cable like this. It includes both data lines and 12 volt power and is available with 2 alternative gauges of power core. The low power version is intended to just drive electronic devices, for example a condition monitoring board, and the high power version has sufficient capacity to drive some hydraulic valves along with some controlling electronics, such as a hydraulic rotor board. This is a hydraulic rotor driving module with 6 sensor input channels and 6 proportional valve output channels. Multiple rotor control modules can be connected in line for additional output channels. We do not manufacture our own hydraulic rotor, but we can advise on design for our customers. Blade profiles for hydraulic rotors are the same as those for the electric version and are available on request. Similarly, this is a reciprocating blade actuator controller. It also has 6 valve output channels, but has no sensor connections as reciprocating blades operate without feedback. There is a gland for an additional 12 volt power feed, which is often desirable as the valves may require more power than can be delivered via the CAN cable. Like the hydraulic rotor module, additional controllers can be connected in line to provide more output channels. This is a 12-channel nozzle controller, which can be used to activate up to 12 nozzle solenoid valves with a maximum nominal current draw of 1 amp per channel as standard, though higher currents are possible on request. Again, these controllers can be linked to provide more output channels. Our nozzle controller will drive any appropriately sized solenoid valve operated nozzle, including latching valves, but for many of our precision applications we found that the existing commercially available nozzles were not appropriate. We therefore developed our own fast-acting precision nozzle assembly, capable of taking a variety of nozzle tips for specialist applications, such as the spot application of glyphosate onto individual plants within high-value crops. Components within the assembly are compatible with most agrochemicals in solution or emulsion form. The nozzle assembly features 2 5mm mounting slots for ease of mounting with a 3D printed housing, to which the nozzle valve and manifold subassembly is clipped in place. A 4mm push-fit connector for spray supply is combined with an integral fine mesh filter to reduce potential nozzle blockages. Nozzle tips can be changed to suit the application, with sprinkler and atomizing tips available. These are also available in different spray angle types for wider and narrower spray applications. Spray pressures can be monitored to ensure that spray lines are at operating pressures, not blocked or leaking, using our spray monitoring CAN bus module. They can be configured to monitor a supply pressure line and 3 spray bar pressures for leak and blockage detection. It is automatically recognised by our software and offers appropriate information displays and warnings. The hydraulic pressure monitoring module is essentially the same unit as the spray monitoring module. The main differences relate to the sensors which are selected for higher hydraulic pressures and include a temperature sensor input. It is also automatically recognised by our software and offers appropriate information displays and warnings. These include supply pressure, return pressure, oil temperature and oil filter blockage. Okay, so that's been a quick run through of our in-row system hardware. We pride ourselves on the flexibility of our system, which is an extension of the robust and well-tested Interrow product. It's a modular system designed for ease of installation and service. Point-to-point cables provide neat serviceable installations to in-row devices. We offer a wide range of sensing options and can control a wide range of output types. Our CAN bus devices add to our capabilities. Its flexibility allows us to add cameras in an affordable way and to operate multi-section machines further enhances performance potential. Our tried and tested touchscreen interface is simple to use and is familiar to operators who have experience with our Interrow products. We hope that you've found this presentation useful. Remember that it's the second of a series of 6 videos that you can select from our website and view them as many times as you want. Our website also has links to other reference and training material. If you have any questions, please get in touch. Thanks for watching.